All right. And just a few minutes ago, I put up kind of a public service announcement on Slack after an incident happened in the hall regarding mask stuff. So when you get a chance, read that. Hopefully it frames stuff reasonably enough. But I'm not going to get into it during class, but take a look at that. I'll also be probably sending out an email and stuff. We don't want computer science students to be part of that, but really any students. So at your leisure, take a look at that note. All right. So homework for in here was to finish doubly linked list, tail pointer probably, right? All right, add a tail pointer to our linked list, which always points to the end of the list. How did that go? Good, bad, horrible? Didn't look at it. My class, my 470 class yesterday lucked out. I had forgotten to put the assignment up, and it was a somewhat tricky assignment. So I probably, I know, a third of the class really struggled with this. They benefited by me not putting it up because I solved it in class and nobody actually told me it wasn't up until like after the fact. I'll punish them later. And then the students who did get it wasted time on the homework at that point, but I think they probably learned something from it and maybe didn't necessarily need the points. But all right, so let's take a look at this. So the tail is something that goes, it's like the antithesis of our head pointer. Okay, so not only are we keeping track of the front of the list, we're also going to keep track of the end of the list. And that can help us in those situations where we were otherwise running from the beginning all the way to the end and then doing stuff related to the end of the list. And last time we already added the ability for our list to be doubly linked, right? Where we can go backwards and forwards. So now it's even more handy. If we can just, through the use of a couple of extra pointers, keep track of the beginning and the end of the list, and we can walk backwards through a list if we wanted to using the previous pointers, that adds some flexibility to something that we've already talked about as being somewhat inefficient. Kind of the beginning of this linked list discussion dealt with kind of arrays versus linked lists and how arrays are relatively fast, but are memory inefficient, whereas linked lists are relatively slow, but memory efficient. And hopefully we're seeing here the amount of time we're spending kind of traversing through a whole bunch of elements of the list that should kind of support that statement of these guys are relatively slow, even though computers are really fast. So hopefully throwing a couple of extra pointers in there, we can see that we're still benefiting. We still have the memory efficiency thing, but maybe we're making our linked lists a little bit quicker, a little bit less slow relative to our arrays. So we're going to go ahead and create another node pointer here, and we'll call this guy tail. And then in our implementation, when we first create a linked list, we will set tail equal to null. Let me save this. All right, but now we need to make sure that when we add stuff to the list or remove stuff from the list, we're also updating tail. Okay, so if we're adding something to the front of the list, if we're looking at the empty list, so it's a brand new list, and we're looking at the empty list, actually, we should probably do it this way. So last time we added this for our previous node, we said, oh, if we're adding to the front and the list has something in it already, we need to make sure that something points back to the previous guy. Otherwise, we're going to set the head equal to this new guy we just created, and we'll set count equal to this guy. Now, inside of add front, will tail actually change? What are the circumstances under which tail should change in add front? Got nothing for me? Go ahead. Okay, but only if we had the empty list. So only if our list started off empty. Is add front and add end basically mean the same thing, right? If we had nothing in our list, then when we add that one thing, which we're doing right now, at that point, head is pointing to that thing, but tail should also point to that one thing. Because if we are adding something to the empty list, head and tail both point to that guy. That one element is both the beginning and the end of the list, right? So this if statement said, should I update a previous node? This guy right here, and I can do that. I can ask this all sorts of different ways. Since I'm keeping track of count, I can say before I update count, I can say if count is currently equal to 0 before I update it. If this was the empty list before, I can go ahead and say this tail is also equal. Actually, we can either say is equal to temp, or we could say it's equal to the same thing as head is equal to. One interesting thing, and maybe somewhat of a confusing thing with linked lists, is we often have several synonyms that mean the same thing. After this line of code right here, this dot head and temp both point to the same place. That makes sense? So we had different ways of talking about the exact same memory address, because all those things, those pointers, we might have 2, 3, 4 different things that hold the identical memory address. So it didn't matter. This question basically says, are we looking at the empty list as a starting point? If yes, make tail point to the same thing head points to. And that works there because we had already updated head. And this question works here because we asked it before we updated count. Make some sense? All right, so for add front, we needed to make sure that we threw in the caveat that, hey, you know what? If I'm adding something to the front of the empty list, tail used to be null. Now I got a thing in my list. I need tail to point to that guy because the head and tail are both the same dude. Okay, so it's our special case for add front related to tail. All right, that makes some sense? All right. Remove front. Now, if we remove front from the list, once again, if the thing we just removed is has left our list in the state of being the empty list, then we need to reset tail to be null. So if we had the one list and now we're removing that guy to now we have the list that has 0 elements in it, we need to make sure that tail gets reset to the value null instead of pointing to a memory address that was just deleted here. All right, so we ask our question, is it the empty list? If it's already the empty list, we don't have anything to change with head or tail. Otherwise, we have something in this list. So we'll go ahead and get the value we're going to return, make temp point at that guy, set head's next node. So we're updating head to ultimately point to who the next guy should be, even if that next guy is null. Then we're deleting the value of temp and all this stuff, and we're decrementing count. So we can ask a pretty similar question here as we did up there. before we decrement count, or actually we would do it after we decrement count. So after we've decremented count, if the count is now 0, the number of elements in my list has now reduced to 0, we can go ahead and set tail equal to the same thing as head, which should be null. Or we could just set tail equal to null, if that makes us feel better. Again, they're synonyms. If my list is currently empty, if I have nothing in there, we know that head, we know that head currently is equal to null. So this line right here would set tail equal to null. So if it did make us feel better, we could do that. Put a little comment in here, reset tail to null if the list is now empty. What we just accomplished there. Make sense? All right, so that's remove front and add front. Any questions on those guys? Now, if we want to test that real quick, what I'm going to do here is I'm going to give myself a little test function. So we're going to say get last. So we'll be able to ask a linked list to give us its last value. Just to see it, just to peek. Make sure tail points at the right place is kind of the idea here. And I'll throw that down here at the, I'll put it right before display. All right. And we'll ask a little question here. We'll say if this tail is equal to null. And I don't know if I've shown you this before, but you can write this exact same thing. I'll just put it above it. I kind of recall I've shown this to you. You can say if not this tail, these two things mean the same thing. Have I shown that to you before? That syntax? It has to do with how nothingness is represented in C and C++. You can say, basically you're asking a question of, does this pointer point somewhere? So this says, if tail points nowhere, if not this dot tail. In fact, if you look at a lot of code examples, you'd probably see that written that way. As opposed to if this dot tail is equal to null. I would say for, inexperienced programmers, this one probably reads a little cleaner, pretty explicit. Like, look, if this dude equals this dude, this is what we're going to do. All right. So I'll go ahead and leave the code here like that, but I'll throw a little comment here. This means the same thing as the line below. Just so you kind of know that. We can ask questions really. You could ask the Boolean question related to memory addresses, is really what I'm saying. Boolean will return true if a memory address exists. It'll return false if it doesn't exist. And we want this guy to return true if it doesn't exist. Hence the reason why we put the not in front of it. All right, so forget last, if tail points nowhere, then we'll just do, am I doing printfs or couts? We'll do cout, no last element. Empty list. else we have something real, and I'm not removing or doing anything. I'm just going to go ahead and return this tail get payload. Just the number, it's at the end of the list. This will be our way of testing. Does tail point to the right dude? Okay. Now for testing this, we'll go into main. And I'm only going to I'll display it there. I did a remove front. That's fine. We display it again. So I'll do a C out. Get last. So I want to make sure I'm only dealing with add fronts and remove fronts, because those are the only functions I've updated so far to be tail aware. All right. So I'll add a bunch of fronts. We'll display it. Then we'll remove a front. And actually, why don't I go ahead and do this before I remove it? Let's just make sure I can print out the last value correctly. That'll tell us whether add front is probably updating things the way it should update things. Then I'll remove something from the front and we'll display it again, get the last element. So that'll remove one thing. And then let's remove 3 more things. So that should get us to the empty list. And then I'll call get last again, which should give us that output that there is no last element. So we're kind of exercising our list a little bit. We'll add 4 things to the front. Well, I guess it's add. Then we'll display it. We've seen that work. We'll show the last element. The last element should be the 1, the guy that was currently is the last element in our list. That's what we'll show here. Then we'll remove the front. So the last element should still be a 1 because we're only removed that 4. So we should still have a 1 here. Then we'll remove the 3, the 2, the 1, which should now give us the empty list. And we should have then updated tail to point to null. So then we'll go ahead and call get last here again. I'm not putting it in a C out because our expectation is it's not going to return anything. Our expectation is this guy is going to give us that print statement saying no last element in the empty list. All right. So this is kind of our little check to make sure our updates there to add front and remove front did what it was supposed to do. The use of this is non-member. Oh, so here, I'll ask the question here. What's my error? My error involves this code right here. That's the thing I've recently added. And look at the message. Invalid use of this in non-member function. We'll go ahead and assume I did this error on purpose. So in case you see this in the future, it'll give you some good input. Anybody see what the error is? Yeah. So I've advertised this get last as being a member of this class linked list. So when you're writing header files, this is kind of like our, hey, this is the stuff we will be implementing. And then here's our actual implementation. But what I didn't do here is I didn't actually do the syntax that links it to our linked list header file to say, hey, this is me implementing it. And realistically, even though I obviously did it on purpose, this could be kind of a simple thing to forget, right? So if you see this kind of error message talking about, hey, I've never heard of the keyword this, it probably means you forgot to link it to your class. All right. All right, take 2. All right, so there's our 1 is the end. Then we printed out the 4 we removed. 1 is still the end. Then we did remove, remove, remove. And then we called get last, which I believe if tail is equal to null, this should have printed some stuff out. So our our remove front isn't quite doing what we wanted to do. So if it's already the empty list, we're going to say you can't remove anything from it. Let me just make sure I'm not doing a remove end in here. Yeah, they're all remove fronts. All right. Otherwise, get the value to return, update stuff, set the next nodes and previous nodes correctly. We'll delete the guy we're getting rid of. No problem. We'll go ahead and decrement our count. Then we're going to ask a question. If our count just dropped down to 0, then we want to go ahead and we want to set tail equal to null. So did my count just drop down to 0? My count should have dropped down to 0. We have a get count, don't we? Get count. Okay, we have a count of 1. So remove front is not working currently for a 1 list, which is actually probably unrelated to tail. It was probably a bug from before. So remove front. If we're dealing with the 1 list and we're going to remove it, let's pretend like that's the case. So we have the head, we'll keep the value. We'll point at that same place. We'll set head to point to head's next node, which will be null. Then we'll set temp's next node to null, disconnecting it. Temp's or head's previous node. Okay, that's where the problem is. We've already updated head here to be null. And then we try to set a null value's previous node to null. We're saying, hey, you nothingness, set your previous node to null. Not going to fly. All right. So we really only. So what's happening is we're actually dying right here. So let's do, I'll take this line. We'll delete temp. Decrement count. If count is 0, we'll set tail equal to null. Head is already to null. Else. Really, we want to just say a separate if. This is a little bit sloppy, but we'll just roll with it. If count is currently 1, we'll set the previous node to null. Our current logic will work fine. Well, actually, hold on. No, it won't. We were never actually updating previous node correctly. So this is correct. Head gets his own next node, set temp, delete temp. If not, this head is equal to null. If head points to a real place, then we're going to set head's previous node I got to do that before I get rid of temp. Hey. Head's going to be equal to his own next node. That's fine, because we're going to remove temp. Oh, no, it's always going to be null. We're not updating who's going to come before it. It's always going to be null. We just need to make sure that this guy's next node, if head's a thing, if this head is not equal to null. If head is a real thing, that means we have a new front of the list, which is a real thing. And since it's the front of the list, that dude's set prev node should be null. So I've updated my list. I have a head points to a new real thing. That new real thing, his previous node points nowhere because he's the front of the list. There's nothing before the front of the list. Else, we're dealing with the empty list, in which case head is already equal to null. We'll set tail also equal to null. All right, if head's a thing, set its previous node to nothing, because there's nothing that comes before the beginning of the list. Otherwise, if head is not an actual element, then we have a zero list. We'll go ahead and set tail also to point to null. All right, so now I should be able to remove front, call get last one more time, and have a count of 0. Here, there's our no last element, empty list, and there's our count of 0. All right, so actually wasn't a bug from this time. That was a bug from last time that we didn't have our remove front properly updating previous node. Which was this guy right here. That line last time was in a bug prone location. Is where it was. Because if we tried to call this head set previous node on a null value, if head was equal to null, we don't get an error. We just don't get the result we wanted. All right, and actually that becomes an interesting thing because that is evidence of the C++ compiler being a newer style compiler. In an older style C++ compiler, we would have gotten a segmentation fault. In doing your any of your homework on here, have any of you seen a segmentation fault down here yet? That's never been an error message you've seen, right? You just get nothing, which is what we've been seeing here in class. Yeah, see, that's kind of unfortunate that it gives you nothing. So when you expect there to be output and you don't see any output, I think as far as I know right now, we should translate that into meaning we tried to access memory that didn't exist. And therefore a invisible segmentation fault, or the Java version of that would be a null pointer exception, has occurred. And they're trying to be friendly here by not giving us output when it's actually, I think, being misleading. I'd much rather have a C style, what's just called a segmentation fault, which basically just says bad memory thing. Don't try to read something from memory that doesn't exist. All right. So in any case, that is our, and we'll leave get last in there. It's not hurting anybody. So we have add front, remove front working now. So now we need to do add end. So add end is kind of like add front for add end related to tail is kind of like add front related to head. So if head is currently equal to null, we'll call add front, which is already working related to tail. We don't need to do anything special in here for tail because this dude's already doing that heavy lifting. We just wrote that. Else, we have a list that at least has one element in it. And n is going to be that last element we just added, right? Just like that. Whoever's going to be the new end of the list, that's who tail's going to point to. All right, so this one was pretty easy. Let's go ahead and just test this real quick. So we'll add something to the end. Let's see, I'll get rid of my remove fronts. And we'll say, LL add end, let's do a 14. So then get last should be a 14. And there's my 14. And we already know it will work for the empty list because we tested add front on the empty list, which is who actually will do the heavy lifting for add end on the empty list. Okay, so that's add end. Remove end. If we're dealing with a one list, we'll go ahead and call remove front, already handling tail. Otherwise, we'll right now to remove to the end, what are we doing? We're running to the end of the list. We no longer have to do that, do we? We have the end of the list. It's called tail. Cur node equal to tail. Then we'll go ahead and grab the value that we're going to be returning. Then we'll set cur node's previous node, next node equal to null. Cur node's previous node equal to null. Now, one thing we need to do is we do need to update tail. Tail is equal to cur node get prev node. I'm about to remove the end of the list, so I want tail to get updated to the dude that comes right before him. And I could say it with cur node here, or I could say this dot tail, because cur node and this dot tail are synonyms because we made them synonyms right there. Okay, set cur node equal to tail. All right, so I've updated tail here. Put a little comment. Make tail, make new tail the second to last guy before we remove him. Then we'll go ahead and disconnect. That's what this guy's doing. And similarly, we could say cur node, get previous node, set next node, or we can just say this dot tail, set next node to null. Because this dot tail now points to cur nodes, get previous node. Tail is that guy, which is the same as that guy right there. So it means the identical logic. Ultimately, we'll delete cur node, knowing that we're deleting cur node that's no longer pointing to the same place as tail points to. Tail points to our new tail. All right. So we'll come in here now And let's go ahead. We'll add 14 to the end. We'll do LL remove end for no good reason. And then we'll say get last again, which should now be a 4. Remove end. I think that's another one of our segmentation faults. Sure it shows it. Oh, see, it's not even showing it. So I think the error is going to be somewhere else. Oh, end is 1. Oh, I was looking for a 4 and it's giving me the answer 1. So it's the right answer. Ta-da! I remember when I was a student, I think I had a situation like that where I remember staring at something for hours when I had the right answer, not knowing I couldn't recognize the right answer when I had the right answer. Doesn't that suck? Hey, see, this is why it's beneficial to have an audience. And obviously another error I did on purpose. It's the way, that's what you can always blame it on. All right, so I think that should handle our tail thing. Okay, so now we have some extra tools to go from the beginning of the list to the end of the list, and also get to the stuff immediately before and after. All good stuff, right? All right, so now here comes our tricky part. Is this our class? Where's all right, so I'm going to steal that, even though it's remove at index. All right, so let's say that this is our, we're going to have remove and add. So actually, why don't we do add at index first? All right, so that's what our, what we're going to try to accomplish. And it's going to be a 0-based index, just like we were working with an array. And I might say, okay, I want to create a new node. I'm going to haphazardly steal this guy. I'll put a little question mark there for where he's going to be, because we're not actually labeling the indexes of these guys. This is just for our, our own visual to see where do they live inside the linked list. And so I'm going to, I'm going to do a 6. And we're just going to assume the memory location for this guy was 211. All right. Get his next node and previous node set. All right. So now what I want to do is I want to add this new node. And let's say we want to put him at index 2. So I've created a brand new node and I want to insert him into this linked list, specifically at bucket 2. I want him to become the new bucket 2, which means he should come right after the old bucket 1, displacing the old bucket 2 to now become bucket 3. Make sense? So the question is how do I accomplish this? I mentioned last class, this is a little bit more intricate surgery. Okay. So if I want him to go after bucket 1, now, first of all, we've actually made this problem easier now by making this a doubly linked list. If we had written added index when it was still a singly linked list, then things get, especially when we don't have tail, now you got to run to 2 different places. You got to get to the point right before him, and then you got to get to the point right after that guy, and then start developing ways of connecting this guy up to those and disconnecting stuff. So having the ability of getting at previous nodes is going to actually make life a little bit easier here. Although it probably makes it more important that you draw the picture, because now we effectively have 4 different pointers that we need to hook up. Actually 6 different pointers that we need to hook up before we finish the open heart surgery. Okay, so here I'm gonna conveniently position this guy a little bit better so I don't have pointers crisscrossing over the thing. All right, so I'm gonna run kernode to this guy right here. Okay. Now I'll go ahead and I'll just label this. This guy is going to be my new bucket 2, which will then displace that guy to bucket 3, which will then make that guy bucket 4, even though in our linked list, we're not actually keeping track of those indexes, right? This is just for our eyes. So I'll go ahead and get kernode to bucket 1. The bucket just before the index that we're trying to insert this guy at. All right, so now what we want, and probably in our code, I think we've been calling it temp or calling it n. Now temp's been the value we're returning. I think n is the new node when we call, like, add something. Oh no, I called it temp there. Called it n there. Oh, that's consistent. Okay, so it's pick your poison, I guess. All right, we'll call it n here. So we just created this brand new node, and this is n. All right, so n's holding on. That's our pointer to that node that's currently just floating out there in the middle of nowhere. So now I need to make n's, since I'm trying to insert it between these two, I need to make n's next node point to the same place that kernode points to. Then I need to make n's previous node point to kernode. So now we've pushed n into the right location, right? So he's grabbing onto the right nodes, so he's part of the chain now. So now we just need to update kernode and n's next node to be correct. So kernode no longer points over here. He now points to n. N's next node's previous node points to n. And now we've effectively added him to the middle of that list. Does that make sense? But you need to make sure you did all that in the right order, because if you disconnected something that you're going to need in a minute, bad things happen. So the order was very important. So as we did each of those steps, you want to go and, move the arrow, go and write the line of code that accomplishes that, as I call them, ninja move. Okay. So question about adding something at a particular index. Call this guy remove an index 2. Keeping in mind that if I say add at index 0, we just call add front, right? If I say add at index 4, we call add end. So basically add at index anything but 0 or count, count -1. We'll follow that strategy I just showed. Remove an index 2. We'll go ahead and set temp equal to 6. So we have been using temp for that. We'll remember the value that we want to return after we remove something. Okay. And ultimately, we want this guy to get disconnected and to disappear. All right. I'm going to position cur node differently. So we'll take cur node and we'll run him down the list to the index that we want to remove. Okay. Now we need, so now we're pointing at this guy. So we won't lose him. Oh, yeah. So we won't lose this guy here because we have this cur node pointer pointing at him. But we need to have the guy right before him and the guy right after him get updated. So we're going to say cur node get previous node set next node to cur node get next node. Cur node get previous node set next node to cur node get next node. It's a mouthful. Then we'll say cur node get next node set previous node equal to cur node get previous node. One more time. Cur node get next node set previous node equal to cur node get previous node. Then we can say cur node set next node to null, cur node set previous node to null, delete cur node, and then these guys have effectively updated to that. See the value of drawing the pictures? Because if you're trying to do that just all off of mental gymnastics, pretty good chance that somebody's next node's previous node's third cousin is going to be lost, right? Okay, so homework. Implement add an index and remove add index in our current linked list implementation. At the self-assessment. It is interesting how hard some of you are on your self-assessments. I'll go and look at your code and it's really not that bad. Like you're one line off, you know, like some little mistake. Oh man, like I deserve a D. No better. If I get any better than a D, it's all right. And then I'll give you a link to our current. I think it probably ends up always being the same link, but just in case. Questions, comments, concerns, bribes. All right, I will see everybody on Monday. And I implore you, draw pictures. Use the slide set, make a duplicate of my thing, and update arrows as you're writing those lines of code. It'll save you hours.